We've seen curl, which measures spin. Now let's meet another operator called divergence, which measures something different. Here's the geometric picture. Imagine a tiny balloon sitting at a point in the vector field. If the field is pushing outward from that point in all directions, the balloon inflates. If it's pulling inward, the balloon shrinks. Divergence measures exactly this, how much the field is spreading out or squeezing in at each point. So the pattern to recognize is that divergence tells you how much a field is expanding or contracting at a point. The formula for divergence is simple. It's just a dot product between del and the vector field f. We write this as divergence of f equals del dot f. To compute it, take the partial derivative of p with respect to x, add the partial derivative of q with respect to y, add the partial derivative of r with respect to z. So divergence of f equals curly dp by curly dx plus curly dq by curly dy plus curly dr by curly dz. The pattern to recognize here is that divergence is three separate partial derivatives, each matched to its own variable, then simply added together. Unlike curl, there's no determinant needed. Now recall back when we studied curl, we found that the curl of a gradient is always zero. There's a matching theorem here involving divergence. If p, q, and r all have continuous second partial derivatives, then the divergence of the curl of f is always exactly zero. That is, divergence of curl of f equals zero. The pattern to recognize is that divergence of a curl is always zero. This gives us a second useful detector. If something is claimed to be the curl of some field, but its divergence is not zero, then no such field can possibly exist. Now let's meet one more operator, which combines two ideas we already know, the Laplacian. Geometrically, the Laplacian measures how smooth or bumpy a scalar field is at a point, by comparing the value there to the average of its surroundings. The formula, take the gradient of f, then take the divergence of that result. So Laplacian of f equals divergence of gradient of f. There's an equivalent formula too. Add up all three second partial derivatives. That is, Laplacian of f equals d squared f by dx squared plus d squared f by dy squared plus d squared f by dz squared. The pattern to recognize is that the Laplacian is just the second derivative in x plus the second derivative in y plus the second derivative in z all added together. Let's bring everything together. Gradient points toward the direction of steepest increase. Divergence measures spreading out or squeezing in. Curl measures twisting or swirling. And the Laplacian measures smoothness. Four operators, four completely different physical pictures, yet all of them are built from the very same simple partial derivatives.